Hello, welcome back. So this section is about working with Taylor series. We now know the Taylor series for many familiar function, and we have tools for working with power series. So the goal of this final section is to illustrate additional technique associated with power series. As you will see, power series cover the entire landscape of calculus, from limit and derivatives to integral and approximation. So let's start with first example. So limit by Taylor series. An important use of Taylor series is evaluating limits. So the first example, evaluate the limit of x squared plus 2 times cosine of x minus 2 divided by 3 times x to the power of 4 as x approaches to 0. So I believe if you recall, I gave you the table for common Taylor series, right? So the common, you can look at that table, cosines of x is from the table for common Taylor series. We have cosines of x. Cosine of x is equal to 1 minus x squared divided by 2 plus x to the power of 4 divided by 24 minus x to the power of 6 divided by 720 plus and so on. All right, this is from the table. I hope you do remember about that. So we know this one. So when I have to find the limit, right, of x squared plus 2 cosines of x minus 2 divided by 3 to the power 3 times x to the power of 4 as x approaches to 0, this will give me the limit, right? I'm going to replace my cosine x with this. So x squared plus 2 times cosines of x. What is my cosines of x? 1 minus x squared divided by 2 plus x to the power of 4 divided by 24 minus x to the power of 6 divided by 720 plus so on. And then let's not forget this minus 2. And everything will be divided by 3 times x to the power of 4 as x approaches to 0, right? So if I simplify this one, like by distributing these two inside, going to go step by step so you get everything at once. So you can see we will have the limit. The top one will be what? X squared. If I distribute these two inside the parentheses, I will have plus 2 minus x squared plus x to the power of 4 divided by 12 minus x to the power of 6 divided by 360 plus and so on, right? Then minus these two divided by 3x to the power of 4 as x approaches to 0. So we can see x squared and this negative x squared will cancel 2 and negative 2 will cancel. So basically, we will be left with the limit of x to the power of 4 divided by 12 minus x to the power of 6 divided by 360 plus this will keep going, right? Divide by 3x to the power of 4 as x approaches to 0. So now, if you have a fraction divided by a fraction, what do? You take the numerator and you multiply by the reciprocal of the denominator. So this will give us what? The limit. So we'll have x to the power of 4 divided by 12 times 3 is what? 36 x to the power of 4. So that will give us 1 over 36 minus x squared divided by 1080 plus, and the power will keep increasing. Do not forget as x approaches to 0. So this limit will give me what? 1 over 36. And that's it. So let's move to the next example. We are asked to evaluate the limit of x approaches to 0, 6 times x to the power of 5 times sines of 1 divided by x minus 6 x to the power of 4 plus x squared. So, again, we will continue. So now, oh, sorry, this limit is at infinity, not 0. Okay. This limit is definitely at infinity. Because I wanted to do one limit at 0 and one at infinity. So, a Taylor series may be centered at any finite point in the domain of the function, but we don't have the tools needed to expand a function about x approaching to infinity. So we don't have that. X is equal to infinity. We don't have that. So we have to use a technique, you know, to change x approaching to infinity to x approaching to a finite number. So, and to do that, um, let me write this one first. So a Taylor series may be centered at any finite point in the domain of the function. But we don't have the tools needed to expand a function about x is equal to infinity. So let's use some substitution. So I would say, you can see we have sines of 1 divided by x, right? So I would just say let, and to get the limit goes to a finite number, so I will just say let x be equal to 1 divided by t, right? Which imply that if the limit of x approaches to infinity, that would be as x approaches to infinity, I mean, or limit, So this also means as x approaches to infinity, then t will approach to what? 0, right? But since it's positive infinity, t will approach to 0 from the right. So now, look, my limit of 6x to the power of 5 times sines of 1 over x, 6x to the power of 5 times sines of 1 divided by x minus 6x to the power of 4 plus x squared as x approaches toward infinity will be the same thing as what the limit of 6 divided by t to the power of 5, right? Times sines of t, right? Minus 6 divided by t to the power of 4 plus 1 divided by t squared as t approaches to 0 now. What did we do? We just replace x with 1 divided by t. And then we can go ahead and make this one the same denominator first. So to have the same denominator, I will have the limit. The common denominator will be t to the power of 5. So we'll have 6 sines of t minus 6t plus t cubed divided by t to the power of 5. So you can see if I substitute t approaching to 0, we'll have 0 divided by 0, which is indeterminate form, right? So we now expand the Taylor series again. We have using the table again, using the table given to you. This will be 0 divided by 0, right? Indeterminate. So we now expand sans t in a Taylor series. Centered at t is equal to 0. So from the table, of common Taylor series. We know sines of t is t minus t squared. Oh, sorry, t minus t to the power of 3, right? Yes, those are odd. Divide by 6 plus t to the power of 5. Divide by 120 minus t to the power of 7. Divide by 5040 plus and so on. So now we will replace sines t in the limit. Okay. So now the limit of, let me write the original one. The limit of 6 times sines of t minus 6t plus t to the power of 3 divided by t to the power of 5 as t approaches to 0 will be equal to the limit, parenthesis, 6 times sines t. My sines t is t minus t to the power of 3 divided by 6 plus t to the power of 5 divided by 120 minus t to the power of 7 divided by 50, 140 plus and so on, right? Close. Then minus 6t plus t to the power of 3. Everything will be divided by t to the power of 5. So now, you can see things will simplify themselves as t approaches to 0 from the right. So let's not forget 0 from right all the time. So now, again, this limit, if I distribute 6 inside, 6t and negative 6t will cancel out. Negative t cube and t cube will cancel out. So what will be left is the limit t to the power of 5, 6 divided by 120, which will give us 20 minus t to the power of 7, 6 divided by 50, 140. That will be 840 plus and so on. Divide by t to the power of 5 as t approaches to 0. So you will see, simplifying this one, we will get what? If you have a fraction divided by a fraction, so this will give us 1 over 20 minus t squared divided by 840 plus as t approaches to 0 from the right. And this limit will give me what? 1 over 20. And that's it. Okay? Now let's move to the next one. So for the next example, that will be about power series for derivatives. Differentiate the Maclaurin series for f of x is equal to sin x to verify that the derivative of sin x respect to x is equal to cosine x, right? So look, oh, sorry, solutions, right? So we will write from the table of common Taylor series. You know, sin x is equal to what? X minus x cubed divided by 3 factorial, which is 6, plus x to the power of 5 divided by 5 factorial minus x to the power of 7 divided by 7 factorial. This is the Maclaurin series for f of x is equal to sin x. And we know this converge from negative infinity to positive infinity, right? And converges at negative infinity to positive infinity by the theorem that we learned on chapter 11. And so since it converges from negative infinity to positive infinity, the differentiated series also converge, right? If you find the derivative, that also will be convergent. Differentiated series also converge for negative infinity less than x, x less than positive infinity. And this will be converged to what? To f prime of x. So now we have to find the derivative of my sin x, right? So look, the derivative of sin of x, which will be what? Equal to the derivative of the Maclaurin series, which is x minus x to the power of 3 divided by 3 factorial plus x to the power of 5 divided by 5 factorial minus x to the power of 7 divided by 7 factorial and so on. I want you to look at this one with respect to dx. This will be equal to what? It will be equal to, what's the derivative of x? 1. The derivative of x cubed divided by 3 factorial will be minus 3 will come down, so that will simplify with 3. So of course it will be x squared divided by 2 factorial, because 3 and 3 will cancel out. It will have 3 times 2 times 1, which is 2 factorial. Same thing here. 5, the power will decrease to 4. 5 and 5 will cancel out, so it will left 4 factorial minus x to the power of 6 divided by 6 factorial, and this will continue. And what is this one? This is equal to cosine of x, and that's it. So you can see the differentiated Maclaurin series for cosine x confirm that f prime of x is equal to cosine of x, right? I mean, for sine of x confirm, so check that. So now let's go to the next one, evaluating infinite series. Use the Maclaurin series for f of x is equal to tangent inverse of x to evaluate. Let me bring this to the next page. Okay, let me pause and write. Sorry, I forgot to write the question down. So use the Maclaurin series for f of x is equal to tangent inverse of x to evaluate 1 minus 1 divided by 3 plus 1 divided by 5 minus and so on, which is equal to the sum from k is equal to 0 to infinity, negative 1 to the power of k divided by 2k plus 1. So again, same thing from the table. Of common Taylor series, right? We have tangent inverse of x is 1. Sorry, tangent inverse of x is x, not 1. X, right? Minus x cubed to the power of 3 plus x to the power of 5 divided by 5 minus and so on plus negative 1 to the power of k times x to the power of 2k plus 1 divided by 2k plus 1 plus or minus, right? Because the sign change all the time, which will give us what? The sum from k is equal to 0 to infinity, negative 1 to the power of k times x to the power of 2k plus 1 divided by 2k plus 1, right? We got this one from the Taylor series. So now, if we substitute x is equal to 1, so we'll have what? Tangent inverse of 1 will be equal to what? 1 minus 1 to the power of 3, which is 1 divided by 3 plus 1 to the power of 5, which is 1 divided by 5, right? And then minus so on, which will be equal to the sum of k is from k is equal to 0 to infinity, negative 1 to the power of k divided by 2k plus 1. Or, of course, you know, from your trigonometry classes, tangent inverse of 1 is what? Pi over 4, right? Then we will set what? 1 minus 1 divided by 3 plus 1 divided by 5 minus and so on will be equal to pi divided by 4. And that's it. In this example, we are asked to identify the function represented by the power series. The sum from k is equal to 0 to infinity 1 minus 2x to the power of k divided by k factorial and give the interval of convergence. So, and this is the last problem we will solve in this section. So solution. First of all, we have to look at this look like Cauchy-Maclaurin series. We know we have to the power of the power is k and we have k factorial. That will remind us to which Maclaurin series, e to the power of x. So we know um, so I will write this is like similar to this is similar to e to the power of x, which is the sum from k is equal to 0 to infinity x to the power of k divided by k factorial. And we know this series converge which converges for negative infinity less than x, x is less than positive infinity. So again, you can see it replacing x with 1 minus 2x gives the sum from k is equal to 0 to infinity 1 minus 2x to the power of k divided by k factorial. Up, 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 up. Okay. K factorial, which is what? Equal to e to the power of 1 minus 2x. And this replacement is allowed because 1 minus 2x is within the interval of convergence, right? Of this series for e to the power of x. That is, so again, for you to show that this is same thing, let me, okay. So we know for e to the power of x, the negative infinity, or let me write, which converges for negative infinity less than 1 minus 2x less than infinity, right? For all x, right? Therefore, because even if you add, subtract both sides, you will still have the same domain. So, therefore, the given series represents e to the power of 1 minus 2x for negative infinity less than x, which is less than positive infinity. And that's it. We stop this class here, and I will see you in the next section.